this format is not going to be quite as nice for the virtual students who actually watch the video, because they're going to have to fast forward a lot because there's going to be a lot more downtime, but that's how it goes. Similar polygons. So you should, and this code will be at the bottom of a lot of the slides. So if you didn't get the code like right now, that's okay. Our learning targets. Students will be able to use similarity statements, which we've already talked about in chapter 4 or 5 in algebra or geometry A, similarity statements. Students will be able to find corresponding lengths, perimeters, and areas of similar polygons. Students will be able to decide whether polygons are similar or not. So instead of doing the warm-up on your own, let's just look at these scale factor problems, which we did last trimester. Does anyone remember when we're trying to find the scale factor, or it was the K value, it's not necessarily a formula, maybe you could call it a formula, but what did we use to find scale factor? Does anyone remember? Well, it was a fraction, maybe not a proportion. We would go the distance from C, this is right in C to what? From point C, I almost said proportion, that was close. The fraction of C to what? P or P prime over top of C to what? Does anyone remember? It was C to P prime over C to P. That would give us our scale factor. So in this case, our scale factor would just be 2/3. Right? And letter B, we could do the same thing with those side lengths. Line segment A prime over B prime. So 25 over the top of line segment AB would give us a scale factor from the blue triangle to the red triangle. So we've dealt with scale factor before, and we're going to talk about that a little bit more today. Order of operations. Okay, review. What is a similarity transformation? Yes?
It has to be like smaller, but it has to be still the same shape and stuff. Right?
Yes. Yep. A similarity transformation. The shape can shrink. Do you remember what that was called? The picture is on there for a purpose. Yeah, it's a dilation. Good job, Tyler. Similarity transformation was our dilation, and we said it was similar because it changed in size. Right? What was the other type of transformation that we looked at? The translation.
Transcription.
We didn't have a transcription. A rotation, a reflection. What type of transformation was that?
Rigid motion.
It was a rigid motion, but it was a blank transformation. What? A rigid is a congruence transformation. No, that's right. Actually, since you got rigid motion, I think it's more difficult than congruence transformation. But these similarity transformations, that would be a dilation where shape grows or shrinks, so it changes in size. And we know the factor that it grows or shrinks is our scale factor. So we're kind of bringing all that stuff back. In case you forgot, this was the picture that we had, or that the book reminds you of. That we have these similarity transformations that change in size. Now the important thing to remember is that the angle size doesn't change. So angle C and angle F are congruent, and all the way through there. And the ratios of each of the sides are the same. Okay, because they're all being multiplied by the same scale factor. Do you remember this? A little bit? Enough? And this is another statement that we already know, but they remind us of in this portion of the textbook. If two polygons are similar, then the ratio of any two corresponding lengths of the polygon is equal. So if we have two triangles, well, let's look at that, just the last slide. With these two triangles, with these two triangles, the side BC and EF proportionally they're the same, right? They're being multiplied by the same scale factor. That's all we're talking about here. So let's see how we apply this to a new situation. Okay, something that we know will apply to a new situation. In the diagram, DEF is congruent to MNP. Find the value of X. With proportions in the back of your mind, does anyone have an idea of how we could set something up to find X? Yeah, Jack.
Well, what I did is I just did like 18.
What do you mean what you did?
Well, like in situations like this,
You shouldn't have done anything yet, so I don't know when you would have done. That's exactly what I talked about right before we started the lesson.
I did it in my head.
This one? Alright, let's let Jack go.
I did this in my head.
Okay.
What I would do is I would just do like 18 divided by 15, and then we get like a number, and then we multiply 20 by like that, see if we get 24.
Okay.
And then I guess we divide 30 by that number to get X.
So what you're talking about is correct and it's on the right track. It's kind of the long way around, but you don't know where I'm trying to go with it yet. So that's good. I like that idea. Mia, do you have anything to add to it? Or a different
I
approach?
don't know if this is right, but just logically,
Okay.
this is what I did. 3 goes into all of the numbers on the bottom one.
Okay.
And it goes into 18 and 15 and just adds another one. So like, and then it goes in, wait,
That's what you're saying.
I got, what did I do? Maybe I didn't.
It's okay. Any other ideas? How can we set something up to try to find what X is? If we know that these two triangles are similar, and that we did a dilation to get from one to the other, how could we figure out what X equals?
So easy, guys.
Alright, what do you got?
Just divide 18 by 15 and then do that number times 30.
There you go. That's good. Which I think that's what Jack said, except in a
choking over it.
longer way. We set up a proportion though. We know, listen up, we know if we have our top triangle, DEF, up here, we need to keep all the proportions that have to do with DEF on top and all the proportions that have to do with M and P on the bottom. So 15 is one of our side lengths in DEF, and that is similar to the side length of 18. This proportion has to be equal to X over, and then which side would be like the similar or the congruent side to EF? Yeah, 30. So if we set up this proportion, we have everything, all the sides that have to do with DEF on top, and that's important to keep everything with the same triangle. Like we couldn't put X on the bottom and 15 up here. We can't be switching things around. Everything that has to do with the sides of DEF has to stay on top and M and P on bottom. But when we set up this proportion, we can solve this. 15 times 30 would give, I don't know, does anyone know what that would give? 450 equals 18 times X. And then if we divide both sides by 18, what do we get? X equals 25. Perfect. And then we can look at our problem. If X equaled 25, would that kind of make sense with those other side lengths? Probably, because X should be our longest side in that triangle. So, setting up a proportion would be how we want to solve this. Another example where we also need to set up a proportion. In the diagram, these two triangles are similar. We want to find the length of the altitude. So what proportion would we set up? We want to find this right here. And we're getting close. Good. We want to find that length right there. So what proportion would we set up to find that? to what? Good. Yep. 20 over x. We need to keep everything that has to do with xpz on top and tpr on bottom. Now, if we switch it all and put the 6 and the x on top and the 8 and the 20 on bottom, that's fine. We just need to stay consistent across the top and the bottom. Now, we cross multiply. 8x equals, let's see, 6 times 2 is 12, and 0 is 120. And what would x equal then? 120 divided by 8, 215. X equals 15, which we can look at it and think, yeah, that probably makes sense. If we got x equals 27, then we probably would have an issue. Questions? Okay, here's where you guys get to practice. So take 3 or 4 minutes. You might not totally finish, but take 3 or 4 minutes, and you can work with someone next to you. You can work on your own. But set up your proportion and then solve for it. Yeah. That also okay, but just so I can see. Then yeah. Yep. A lot of times it's not as obvious as just times 2, like it's 1.5 or something like that. Yep, that works. Did you get logged on? Found the problem? You need help or don't need help? Oh, good.
Oh, look at that. I got a doll stand.
I can open up class kick, so if you guys need help, you can still. Why do I need a class kick? I'm the one that.
Wait, do we do all the questions or just?
Nope, just that slide. Good question. I mean, if you get done, like, I just don't want you to work on the other slides while I'm talking. Okay? Like, right now, we're supposed to be working. If you finish it on early, you can go. Yep. Yep. Yeah, there are a couple ways. Like, you can set up. Oh, sorry. So probably. So you got, right? 42, is that right? All right, I'll check just like it will. We'll go about 1 more minute. Oh my goodness, why? Yeah, 42 is correct, Ethan. 42. Yeah. So, I guess you don't have to multiply, but that's how you probably see me set up. No problem. Okay. Yeah. Yep. Yep. Which, I mean, that's you're doing the same math that you would do when you set up a function. But if that's the way that it makes more sense to you, to look at it, yeah, it's totally fine. overall, like for we keep 23 students, so there's probably most of them time. So it's easiest we can do it every time. Where it gets tricky is if it's like, what's the answer to 0.7, like something else. What? Number 4. 46. All right. So we will keep moving forward. Or does anyone? Why don't we talk about the answer? Does anyone have an answer for number 2? Yeah. 8. Do we agree? I think I agree. What about number 3? Why is this not on the I'm still trying to write 8. What did you get, Kaylee? Yeah, I saw a couple people in the back row and around. They got 42 as well. That's good. And if you have questions about those, then you can talk about those at the end. If you didn't finish, you can finish those at the end. So here's our first theorem of this chapter. Perimeters of similar polygons. We're going to look at, we just looked at the proportion of those side lengths. But really, the new stuff today, the difficult stuff today, is looking at perimeter and area and how that changes with different polygons. If 2 polygons are similar, then the ratio of their perimeter is equal to the ratio of their corresponding side lengths. Okay? So our corresponding side lengths is if from LM to QR, we go from 4 to 8. And our ratio of the corresponding side lengths is times 2. Our scale factor is 2. That means that the ratio from the area of the blue to the area of the red will also be 2. So those ratios are the same. That's all that it's talking about. And that would be the finding perimeter. So when you look at this example, a town plans to build a new swimming pool. An Olympic pool is rectangular length that is 50 meters in a width, or has a length of 50 meters and a width of 25 meters. The new pool will be similar in shape to an Olympic pool, but will have a length of 40 meters. So our new pool, this draws, says we'll have a length of 40 meters. I don't know why this is having such a hard time with it. Find the perimeters of the Olympic pool and the new pool. So what we would look to do when we set this up, we know that the perimeters and the side lengths have an equal proportion, right? We don't have to do anything special before we find the perimeter, which is not going to be the case with area. So if we're setting up our proportion, the Olympic pool has a side length of 50. And which side of this new pool does that match up with? Or does that correspond with? 40. Now this is a solid 10 seconds. Maybe. Now, what we would like to set up in our proportion is the proportion of those, or a fraction with those lengths, and set it equal to a fraction that represents the perimeter of each. So if we look at the Olympic pool, could we find the perimeter of that pool? The Olympic pool, the one on top.
Yeah.
Yeah, we could. And what is the perimeter of that?
100.
Yeah. Now, would we want to put that 150 for setting up our new proportion on the right-hand side of the equation? Would we want to put that on in the numerator or denominator?
Numerator.
Yeah, we want to put in the numerator because the 50 goes with the Olympic pool, so we need to stay consistent and keep everything that has to do with the Olympic pool on top. Now, do we know the perimeter of the new pool? No, because we don't know this side length. Now, the question didn't ask us to find the side length, right? We do know?
25. They never said they changed it.
Well, they did say they changed it because they said the new pool will be similar in shape. So if the length changed, then the side changed too. Good try though. We don't know the perimeter though either, so we can just call this
Probably 15.
D. Could be. Now, can we solve this? Yeah. What's 40 times 150? It's got to be something pretty big number. What?
6,000.
Is it 6,000? Did I set up something wrong? We'll see. I might have set up something wrong. What is it? 6,000?
6,000.
And then we need to divide that by 50. What do we get? 56,000?
No.
Yes. 120?
6 million.
Something seems off.
That's terrible.
Oh no, good job. Who said 120? It was one of you two. I don't know who got it on the screen. Oh, it's Hannah? Perfect. Really? So, do you guys see how we set up our proportion? We can find that perimeters.
Yeah.
Perimeters has the same proportion, same scale factor as the side lengths do. I think this is the part where you then really strong. Where you go on to the next problem. Yeah, go ahead. 2 gazebos. Find the perimeter of gazebo A. Now you could set up a proportion and find each of the sides of gazebo A, but that would take forever. So you might want to just set up a proportion. Find the perimeter like we did in the last one. More seconds. Well, that would give you then, right, that would give you that, so then if you keep just you could find each one, yeah, and then just add them up. Or you can set up like I did on the board and set up the proportion of those side lines. So we know that has to be equal to the proportion of the perimeters. So we found the perimeter of the one we know, gazebo B. When they put that X there, like right by AE, that makes it kind of confusing because you don't need that. So I do get why you do that. What is X equal?
Wait, no, sorry. X.
Oh, sorry, not X. What does yeah, perimeter. That's what I meant to say. I don't know why they put X on it, because X doesn't. We should find that the perimeter of gazebo A is 46 meters. Do we have questions on that? Yeah.
How would you get 5 over 10?
That it wouldn't. I tried to write 15, but it wouldn't write it. Oh, that's right. So it should be 15 over 10. Like I wrote on the board. Good. Yeah. All right, one more idea to look at with these proportions, and it's different than what we had before. With area. Now with perimeter's nice because we can take the proportion of, or the side lengths that are proportionate, set them equal to the perimeter that we want to find. Now with area, we have to do a little bit more work. If two polygons are similar, then the ratio of their areas is equal to, so the ratio of their areas is equal to the squares of the ratio of their corresponding side lengths. So we can set up a fraction with the corresponding side lengths. What we have to do to those side lengths is set it equal to the area.
Square.
Yeah, we have to square. Square, which kind of makes sense, right? Area is like 2 to the second power, it's squared. Maybe not as much as this. Anyway, I think the best way to look at this will be with an example, if the slide will ever go there. So here's how we would find, well, you tell me, how would we set up a proportion to find the area of, what do we want to find? Area of DEF. What do we think? We know that the sides, the proportion of the sides, or a fraction with the sides, has to be squared. Let's just set it equal to the area. Yep. Now, that would work perfectly if we were, I don't know why it's writing 0. That would work perfectly if we were finding perimeter, but what do we need to do to this 10 over 5 in order to be able to set it equal to the area? Find equal. Well, what did you guys just tell me on the last slide? We had to do.
Square.
Yeah, we had to square it. 10 squared. Can we solve this? With our exponent rules that we learned in algebra. What do we do with this? Well, we can simplify this fraction, right? This would just be 2, and then we can square it. But if this were like 7 over 5, something we couldn't simplify, what would we need to do with this exponent? We can distribute it. This is one of our exponent rules that you learned last year, hopefully. We could rewrite this as 10 squared over 5 squared. Now, again, since it's 10 over 5, we just simplify that to 2 and we square 2. But if you had like 5 over 7 or something, then you would need to distribute that 2 to each of the numbers. You following with me? Following with me? Okay. 2 squared gives us 4, so really we still can set up, I would at least still set up a proportion. 10 divided by 5 gives us 2, 2 squared gives us 4. I'd write it as 4 over 1 and cross multiply to get rid of this fraction. That seems too... Oh, no it doesn't. And what would x equal? 9. Yep. Which in area of 9, I mean, we're going from a larger triangle to a small triangle. So having an area of 9 is believable. That would make sense. What questions do you guys have besides Braden? So what we looked at today, we looked at how to find side lengths, right? Setting up a proportion to find side lengths. We looked at how to find proportions to find, set up proportions to find perimeter, right? And we looked at how to set up proportions to find area, which was that last one. Why don't you go ahead and finish the Google Slides? Any of them, I mean, go back if you need to, but there should be one more, new one, that you need to finish. Once you are done with a slide, why don't you raise your hand and I'll go through and check it. But once you have all your hands raised, you don't have to wait for me. You can go on to Big Ideas and start the assignment. So the assignment is not due today. We will take some time to work on it tomorrow as well. First couple minutes of class. Yes, Kaylee?